So in this video, guys, we're going to talk about electric and gravitational fields. Fields come up a lot when you study physics, and they're a very useful concept to have. The idea of a field is that an object has some property and it changes the space around it in some way, shape, or form. And so the two types of fields that we're going to look at are electric and gravitational fields, with gravitational fields being produced by masses and electric fields being produced by charges. So to start off with, I want to look at gravitational fields. I think that you probably have a better feel for a gravitational field because you can literally feel it with your own body. Since you have mass, you experience the force of gravity. And so when we talk about a gravitational field, say we have some planet, and I'm going to call this, be original here and call this planet P. So we have our planet, and then we have a mass somewhere, say maybe right there. Okay, so we have our mass some distance away from the center of the planet. Now, there's a couple ways that we can calculate the force of gravity on this mass. So the idea is that the planet has mass. It changes the space around it, and because of that, another mass will experience a force, and we say that this is due to the force of gravity. And when we calculate the force of gravity on the mass at this location X, we said, and we did this at the very beginning of the course, we said the force of gravity is equal to the mass times what we call the acceleration due to gravity, little g. Well, it turns out that what this acceleration due to gravity is, this little g, it's a measure of how strong the gravitational field is at that point in space. And so, say that this had a value, this little g had a value of 5 meters per second squared. Well, that's the same as saying that the gravitational field has a strength of 5 newtons per kilogram. Just to kind of prove it to you, a newton is equal to a kilogram meter per second, and if you divide that by a kilogram, the kilograms cancel out. Sorry, it's a kilogram meter per second squared, mass times acceleration, right? And so the kilograms cancels out and we get our acceleration. So rather than thinking about this as an acceleration to gravity, we can think of it as the strength of a gravitational field. And what I wanted to point out is that we can calculate this force by taking the property that interacts with this field that permeates throughout all of space around the planet times the field strength. So mass times field strength gives us force. And we're going to see something very similar to this when we talk about electricity. So if we have an electric field, we can also use it to measure or calculate the force on a charge due to interaction with this electromagnetic force. So instead of having a planet, maybe we'll have a positive charge right here. And again, we'll have some distance away from the positive charge. And we recognize that because this has a charge, it's going to change the space around it in some way, shape, or form. And so if we put another charge, I'm going to call this charge little q. We use, remember, with Coulomb's law, we use q a lot of times for charge. So what we say is we put a small test charge here, okay? And if I want to know the force, the electric force on this little test charge Q at this point X, I can say something, instead of having the mg, I'll say it's Q, okay, so the charge that exists at this point X, times the gravitational field strength. Sorry, gravitational. Times the electric field strength, okay? This does have a direction. We'll get to the vector nature of this pretty soon. But notice that I'm doing something just very similar. So back with gravitation, I had mass times the gravitational field strength, little g, and I got a force. When it comes to electricity, I have charge times the electric field strength, gives me force. And so this is really the equation of the day. Okay, so this will, if we know the gravitational field strength, if we know the electric field strength and we know the charge that exists at the point in space, then we can calculate the force that charge is going to feel instead of using Coulomb's law. So Coulomb's law is analogous to Newton's law of gravitation for electricity, and this is kind of the other way to calculate the force on a charge, is using this idea of an electric field strength. Okay. All right, so we have this idea that these fields permeate through the space, either due to a mass in the case of a gravitational field, or due to a charge in the case of an electric field. And we want to have some visual way of representing the field strength. Okay, we don't want to have like a number here, a number here, a number here, a number here, because the fact is every point in space, has a field value to it. If you're talking about a gravitational field or an electric field, if there's a charge around. So instead what we do is we use these things called field lines, and we have some conventions of them. Okay, so first of all, the field lines, you'll see these, okay, and so maybe you'll see a set of field lines that look like this. I'm going to curve this one out a little bit, and I'll curve this one out, okay, just to make something more obvious. So you'll have these field lines, okay, and the idea is that the force on an object so if you go to this point right here and put, just for simplicity, I'm going to start using charge. So say that these are electric field lines, and we have a charge here, then the force on this charge would be tangent to this field line, okay? And that's any point along here. The force on a charge at that point on the field line will always be tangent to the electric field. Okay. The other thing that you'll see with field lines is you'll see these little arrows. Okay. That represents the direction of a force. And with electricity, that gets a little tricky, which I'll explain in an upcoming slide. But you'll also see these little arrows. So these arrows denote the direction of the field that exists at that point in space. And I want to reiterate that fields are indeed vectors. So if I had, say, a charge here, and I had, our charge here, right? So maybe the field due to this charge, say I have a charge Q, the field due to this charge might be pointing away. Okay, I'm going to call this EA, which is an evil video game corporation, but it works. All right, so there's charge A. And then maybe this is B. And so EB would be pointing maybe this way, okay, because that's going to be pointing, if I have a positive charge there, it's going to point in the opposite direction. Well, the net field will be the vector sum of those two vectors. Okay, so the net field, change colors here if I can. I'm not sure if it'll let me. Oh, it does. Oh. So the net field, go back, will be going maybe in that direction. I can't believe it just changed colors on me. Anyway, so the net field will be going in that direction. Okay. So it is a vector sum. And then finally, with these, go back to right here. The closer the lines are to each other, the stronger the field. So just visually, what you can see is the closer the field lines, the stronger the field in that region of space. Okay, so you can see the spacing. These lines are closer together than these lines over here, and so we would have a stronger field at this location than we would at that location. Okay. All right, now I've been kind of glancing around an issue, and you may have realized it, is that gravitational fields, they will always point towards the mass. Sorry, it's a positive charge. They will always point towards the mass that's creating. So if I have a mass and it's creating a gravitational field, the field will always be pointing towards it because it's attractive. Okay, so this is the point. This is what gravity does. Well, electricity's weird, okay, in that I have a positive charge, and the question is, well, what direction is the field going in? Well, if I define the direction of the field as being the direction of the force on a charge, it begs the question, well, that's fine, but what type of charge do we use to define the direction? Because if I have a positive charge here, and if I have a negative charge here, okay, this charge, okay, negative Q, feels a force going that way, and the positive charge feels a force going the other way. And so we have to make this choice. How do we define the direction of this field? And the convention that was chosen, over 100 years ago, maybe even 200 years ago, but well over 100 years ago, the convention was that we'll define the direction of the electric field based on the force on a positive charge. Okay, so if I were to draw a field line, if I were to draw the field lines around a positive charge, I'm going to move over here now. These field lines would be pointing out away from it because a positive charge at that location in space, this little positive charge will feel a force pointing away from this positive charge. And so what this means is that plus charges experience a force in the direction of the field around space here, and negative charges experience a force in the opposite direction from the field. Okay? This is important to keep in mind, guys. Okay, this tends to confuse a lot of students. So they'll see the field lines, they'll see the field, and they'll have a negative charge, and they will think that the force on the negative charge will be in the same direction as the electric field, and it's not. It's going to point in the opposite direction from the electric field. So the long and short of it is that field lines are a great visual representation of it, but with electric fields especially, you got to be careful about the direction. These directions are only true for positive charges at these locations in space. Now this picture that I keep on bopping back to, but this picture, if you think about it in 3 dimensions, it's they're really, really kind of pretty. So say that this green is a positive charge, and this red is negative charge. It doesn't really matter what they are. Well, the space between them will be the sum of these two fields, right? So this field, the green field, I'm trying to get my green back. So maybe at this point, the green field will point in that direction because this is positive, right? We said that this was a negative charge over here, okay? And so the red field, the field to the red, at that point in space, okay, if I put a positive charge there, it's going to feel attracted to a negative charge. And then the sum of the two will be along the field lines that we see. And so the sum of it all, and all these field lines, you can see, make this really, really pretty, kind of curvy, 3-dimensional thing. Okay, I always thought these were really neat. Okay, but yeah, so this is what the electric field between two opposite charges would look like, and the electric field between two like charges, one will go this way, one will go this way. It actually cancels out, and it kind of like curves up like this. Okay, if they're like charges. All right, so hope this was helpful to you guys, and I hope you guys took good notes. And we will go over this more in class.